Let's start with the basics. An inductor is a fundamental electrical component that stores energy in a magnetic field whenever electric current flows through it. Picture a simple coil of wire. This is essentially what an inductor is. As current passes through the coil, a magnetic field is generated and concentrated by the shape and number of turns in the wire. Inductors are found in countless electronic circuits, serving roles such as filtering signals, storing energy, and matching impedance between different parts of a circuit. Their ability to resist changes in current makes them crucial for stable circuit operation. As we move forward, we'll explore how inductors work, their key properties, and their practical applications. When current flows through a wire, it creates a magnetic field around it. In an inductor, which is a coil of wire, this magnetic field is concentrated and strengthened. The more turns the coil has, the stronger the magnetic field becomes and the greater the inductance. Inductors naturally resist changes in current. If the current tries to increase, the inductor generates a voltage that opposes this rise. If the current decreases, it tries to maintain the flow. This property is vital for many circuit functions such as filtering unwanted signals, storing energy in power supplies, and generating frequencies in oscillators. Inductors are also used in transformers and chokes to manage electromagnetic interference. Inductors come in various types, classified by their core material, such as air core, iron core, or ferrite core, or by their construction like toroidal or cylindrical shapes. The key property of an inductor is its inductance, measured in Henry's H, which quantifies its ability to store energy in a magnetic field and oppose changes in current. Another important concept is inductive reactance, which describes how inductors oppose the flow of alternating current AC, increasing with frequency. Inductors can also be categorized by self-inductance and mutual inductance, which we'll discuss in detail next. Understanding these types and properties helps in selecting the right inductor for any electronic application. Self-inductance is the property of a coil that opposes changes in its own current. When the current in a coil changes, it creates a changing magnetic field, which in turn induces a voltage within the same coil. This is called back EMF. For example, if you try to increase the current through a coil, self-inductance generates a voltage that slows the rise. Conversely, if you decrease the current, it tries to keep the current from dropping too quickly. Mutual inductance, on the other hand, occurs when two coils are placed close together. A changing current in one coil induces a voltage in the other, which is the principle behind transformers. The strength of this effect is quantified by the mutual inductance coefficient. Inductors can be connected in series or parallel, and their total inductance depends on the configuration. In series, the total inductance is simply the sum of all individual inductances. In parallel, the reciprocal of the total inductance is the sum of the reciprocals of each inductor's inductance. When mutual inductance is present, such as in closely coupled coils, the total inductance changes depending on whether the coils are aiding or opposing each other. In series aiding, mutual inductance adds to the total, while in series opposing, it subtracts. The same principle applies to parallel combinations, but the formulas are more complex. These combinations are essential for designing filters, transformers, and other advanced circuits. The coefficient of coupling, denoted by K, is a dimensionless number that tells us how effectively two coils share magnetic flux. If K equals 1, all the magnetic flux from one coil links with the other. This is perfect coupling, as seen in ideal transformers. If K is 0, there's no coupling at all. In real-world applications, the coefficient of coupling helps engineers design efficient transformers and inductive devices by maximizing energy transfer and minimizing losses. The formula for the coefficient of coupling is K equals \frac m \sqrtl1 L2, where m is the mutual inductance and L1, L2 are the self-inductances of the coils. Understanding this concept is key for advanced circuit design.